So in this video, we're going to talk about electrophilic aromatic substitution reaction. And we're going to break this down into three different parts. The first part, we're going to talk about the reactivity difference between an alkene and an aromatic system. The second part, we're going to look at the general mechanism for an EAS reaction. And the last part, we'll look at a specific example. So if we focus in on the reactivity difference between a typical alkene and an aromatic system, if we treat both of these with Br2, we know the alkene undergoes an addition reaction to add two bromines across that pi system. However, if we do the same reaction with benzene, we see no reaction. However, if we add to this system now a catalyst, iron tribromide, this activates our Br2, and we actually see some chemistry happen. In this case, one of these hydrogens gets substituted for the bromine. This is an example of our aromatic substitution reaction. Electrophilic aromatic substitution reaction. In the next part, we'll look at a general mechanism for the EAS reaction. So now let's take a look at the general mechanism for an electrophilic aromatic substitution reaction. Here we have a benzene ring, and we're going to react this with a general electrophile. And what happens is the aromatic system is going to attack that electrophile, and that's going to break up our aromatic system and give us a carbocation. Now this is a resonance stabilized carbocation. However, we did have to break up the aromatic system to do this reaction. In the second step of this mechanism, a base in solution is going to grab this hydrogen, and then these electrons are going to be used to remake that aromatic system. So we remove the hydrogen here in order to get that aromatic system back. And now we can see that we've replaced the hydrogen that was at this position with our electrophile. So this is a generalized mechanism for an EAS reaction. Let's look at a specific example next. All right, so let's take a look at a typical example of electrophilic aromatic substitution reaction, the bromination of an aromatic system. So here we have benzene, we're reacting with this Br2 and a catalytic amount of iron tribromide, and we've replaced the hydrogen with one of these bromines. One of the important things that happens in this reaction is actually the activation of our Br2. Remember, Br2 on its own was not reactive enough for this chemistry. However, the Br2 can react with our iron tribromide, which is a great Lewis acid, and what we get out of this is now a really reactive species. So this part here, the bromine with the iron, is a really good leaving group. So this bromine becomes a really good electrophile. We're going to use this electrophile in our EAS chemistry. So if we take a look at our mechanism, the same thing is going to happen as we looked at in our general mechanism. The aromatic system is going to attack this bromine, kick off our leaving group. Now we've added that bromine to the ring system, and we still have iron tetrabromide in solution. And this is going to act as our base to pull off our proton and give us our aromatic system back. So these electrons are going to grab this hydrogen, reestablish that aromatic system, and give us our product. So we end up with our arobromide. We get our catalyst back, and the other byproduct that we get is HBr. So this is an example of a typical electrophilic aromatic substitution reaction. The difference is going to be, as we look at other mechanisms, is the electrophile is changing, and how we're activating that electrophile is going to be changing. Hopefully you found this useful when you're starting to study your electrophilic aromatic substitution chemistry.